Thank you. I'm very happy to be here. It's been a really interesting conference hearing everybody's talks. I'll also say I was here at Berkeley as a postdoc after getting my PhD from Stanford. So I'm actually a Stanford and Berkeley alum. I don't have an endorsement from the governor yet, but it's always great to follow Richard Allen and his talk about earthquake early warning. It's a hard act to follow, but what I wanted to talk to you about today is the work that we're doing. It's a very different type of technology and data that we're looking at. It's satellite-based radar. And as Greg introduced, it is a project that I've been working on for the last 10 years or so with a lot of people at Jet Propulsion Lab in Pasadena, as well as researchers at Caltech. So what are we talking about? So the type of data that we've been looking at is called synthetic aperture radar, and most of the work that we're doing is looking at interferometric synthetic aperture radar. So for that, we shorten that, since it's kind of a mouthful, to INSAR. So that's like the first acronym I'll explain today. And hopefully I will try and avoid doing too much NASA speak, but definitely ask me questions if there's things that I explain that I don't explain well in this talk. And don't explain the technical aspects. So what you're seeing here are two examples from two different earthquakes where we've used satellite-based radar, INSAR, to measure the total deformation caused by the earthquake. So this isn't, the strong motion, it's not the high frequency motion, but it's the net deformation caused by the earthquake. And what's great about what we can do with synthetic aperture radar is that we can see very easily the total deformation, particularly in areas where there might not be as good ground-based sensors. So for instance, in the Nepal earthquake, there were a few GPS stations there to measure the total deformation and some seismic stations, but from space, we don't necessarily have to have that in situ network. So areas that might not have the infrastructure to measure that, we can measure that using synthetic aperture radar. One of the things that was an important result of looking at that radar data from Nepal was there was this question about whether or not the earthquake had ruptured up to the surface. And that was in a fairly remote area of Nepal. And from space, we can easily see that relatively quickly. Another aspect of radar data that has been a benefit that has been acknowledged is demonstrated by the result from the earthquake in Mexico, one of the two earthquakes in Mexico in 2017. The image there is again showing the net deformation movement caused by the earthquake, and then the epicenter from the earthquake. So the initial epicenter from the USGS NEIC, because it was from a global network of seismic stations, you can see that it was relatively far off, and the local epicenter from the seismic stations in Mexico was a lot more accurate. The radar data was able to confirm that most of the deformation was centered underneath the epicenter from the Mexico local network, and so we can use the radar data, if we can get it rapidly enough, to help refine the location of that earthquake and also help give information about where that rupture has occurred. There was some local faulting from the Nepal earthquake. That picture that you see there is from Roger Billam looking at some ground rupture caused by the earthquake, but that was actually caused by localized shaking and liquefaction. So that's another aspect that radar can help with, is helping to identify where the ground has ruptured. It's a little difficult to see in these images from the radar data, but there's another way to visualize the data that more easily highlights where the ground rupture has occurred. Another aspect of the radar data that we can use to help with earthquake response, and this has been pioneered by a person at JPL called Sang-Ho Yoon. He's really tried to look at how the phase return from the satellite has changed in such a way that we can identify damage caused by the earthquake. And so synthetic aperture radar has been used since about 1992 for science to look at the surface deformation of the Earth. In the last decade or so, we've really been looking at where you can't actually measure the surface deformation because of great change in the reflectance properties as a proxy for damage. You realize that when a building collapses, you can't measure the deformation across that area if there's a lot of building collapse because the phase return becomes incoherent. But that's actually information about where the buildings have collapsed. So he's been developing these maps that we call damage proxy maps and has been producing them in response to various different disasters, earthquakes, hurricanes, floods, as a way to help inform people as to where the damage has occurred. And one of the advantages from synthetic aperture radar compared to, say, optical data is that synthetic aperture radar tends to be collected over a much larger area. And we can automate the damage assessment. So in this figure here, on the left, all those little yellow bright spots are areas where we see that there could be potential change that could be damage. So we can quickly image a very large area. With optical data, you're typically looking at much smaller areas, and it takes a lot longer to collect data over this large of a region, as well as to analyze it. It's a lot harder to automate the analysis of change detection in optical data. And so the combination of radar data and optical data can be really powerful because you can use this map to focus your optical imagery collection as well as your analysis to look in more detail in particular areas. The other advantage of radar I'll point out it's not so useful for earthquakes, but it can be occasionally. It's very useful in storm damage detection is that radar can see through clouds. And so in storms, there's a lot of damage that occurs, but the clouds don't clear until days later. Radar does not have the limitation that optical has in that it can image through cloudy weather. So the other aspect of the ARIA project is to work with the agencies that can use this information to inform them of what these types of images are so that they can help use this information to dedicate resources where they should go. So in the aftermath of the Nepal earthquake, we worked with the USGS and NGA to explain these damage maps to them so that they could use it for deploying search and rescue teams. And so that was one of the first examples of where the data that we collected had been used for disaster response. So because there's going to be more and more of this synthetic aperture radar available to the community, the ARIA project, this Advanced Rapid Imaging and Analysis project, our goal is to help automate the analysis of this data. A lot of the work that's been done, there's been a lot of research in different universities, different centers, it's still ongoing. It is kind of handcrafted results that is difficult to replicate and difficult for response groups to really get used to using in a reliable way. And it also, what we've learned over the years in this ARIA project is that disasters always happen on Friday night. And so the more that we can get automated, the more that we can have the computer do the work, the better. Not only for being able to produce things rapidly, but also for being able to scale up the work that we're doing on this. And so, we thought about this 10 years ago. We saw the future of more and more data becoming available. We said, we have to get started now. And I think the one thing we've gotten right is that, yes, it's going to take us a while to get this right. We're still working on it. But this image here kind of shows the overall goal of the ARIA project, which is to automate the data collection and the processing, to develop these actionable data products from the data. People within the research community, obviously we like to show things in a way that we as scientists understand, but that's not often the information that people who need to use it for damage response or disaster response need it. So we've also been engaging with a lot of different agencies that are play an important role in disaster response to try and develop those products and explain to them what SAR can do for them, and then take that back, get their information needs, and then take that back and develop the right products. So one of the, going back to monitoring surface deformation, we've been working more recently on automating the production of surface deformation data using a satellite that the Europeans have launched called Sentinel-1. And these are just some examples of some of the results that we have from this automated processing that kind of shows you that you can see how the ground is moving in areas that might be familiar to you. So we've got velocity across the Bay Area, and you can see the change in the velocities across different faults. So this type of technology can be used to map slow fault creep. We also have deformation rates in the Central Valley. And there in the Central Valley, most of that deformation is subsidence that's being caused by the groundwater being removed from the groundwater aquifers. And one of the things that, when we talk to the Department of Water and Power, when we talk to different agencies, and we've also talked with the Department of Homeland Security Critical Infrastructure Group, they're really interested in where this type of deformation overlaps with critical infrastructure, because there have been cases where that subsidence due to the groundwater aquifer withdrawal is affecting local infrastructure. And obviously, fault creep impacts local infrastructure as well. And so this is a new way, a relatively new way of being able to monitor this from space. And there's also an example looking at a more dramatic deformation related to Hawaii in Kilauea volcano. Another key application for this type of technology is looking at subsidence along the coast. So this is an example from David Beckert, research scientist at JPL, who has looked at the Sentinel data and looked to see what type of subsidence is happening within Hampton Roads area in Virginia. So this is on the East Coast. This is an area where there's a lot of infrastructure, there's a naval base, there's a lot of people living in this region, and it's being affected by sea level rise. One of the things that is really changed over the last year or 2 years too about how we can use this data is there's finally enough of it from the Sentinel satellite that we can start to talk about uncertainties. That's something that's been missing for a while, and we're still wrapping our heads around in terms of how do we accurately communicate and estimate the uncertainties in the SAR data. It's been largely used in things that have fairly large displacements, like earthquakes or volcanic eruptions. But we want to get more and more into being able to monitor slow rates of deformation associated with sea level, or that could affect areas impacted by sea level rise. We're not the only ones doing this. Like I said, there are a lot of groups that are in this area. This is a particularly exciting project that we've heard about within the community that I just wanted to show in terms of what is here and what could be coming in the future. This is some figures from the Geological Survey of Norway. So they received funding to take the Sentinel data and generate a vertical land motion map of the entire country of Norway. Why did they do this? They are worried primarily about landslides. So this has been very useful for them to identify areas that could be affected by landslides. But it's also applicable to localized subsidence within urban areas. So this is something that if you go to their website, they have a map. There's a little screenshot of the full country map there in the lower right-hand corner. You can click on a dot. You can see the time series. If you go and you look at that, you'll see that there's gaps. They have snow in Norway. Radar does not work in snow. And so they do have some gaps there. But this is really one of the first demonstrations of making something like a vertical land motion map publicly available for everybody to use. And it's excited a lot of people. They're getting funded to do this across all of Europe. We're talking to people within the US and the USGS about how do we do this in the US. So going back to damage assessment, wanted to show a little bit more examples and dig a little deeper into some of the issues that we're trying to work on there. And so this is another example of how we've taken the radar data and done an estimate of the damage. This is following the 2017 Hurricane Maria in Puerto Rico. The damage assessment map that was generated was handed to FEMA FEMA took that, aggregated it with other information, and created this damage density map that was used in order to identify where the resources were needed, where the high priority resources were needed. And again, this information was really important, even though it was provided days after landfall. It was still one of the earliest bits of information that they had from Puerto Rico because there was still a lot of cloud cover. And so the optical resources weren't really showing them anything yet. As you might remember, a lot of the power and communication was out in Puerto Rico. So they weren't getting a lot of information back. And so this was particularly useful. So over the years, we've done a lot of different work in many different areas and had diverse set of responses with diverse sets of end users. And this slide is kind of a slide just to show that, hazards are really global and radar can work in many different environments. And so, we have worked on volcanic response. We've worked in different areas that have experienced floods. We've also worked with different types of data. So I've talked a lot about Sentinel. That's been one of the best data sets for synthetic aperture radar, but there are other sensors out there. We worked a lot with an Italian constellation called Cosmos SkyMed that was really useful. And so one of the things that is also coming in the future is more satellites and more different types of data. So learning to deal with this heterogeneous data set is also important. More recently, this slide is a little easier to interpret, just to highlight some of the more recent responses that we've worked on. We did respond to the Ridgecrest earthquake, and there you have the deformation data with the fancy colors. So this figure showing the deformation data, that's displayed in such a way that it's easier to see where the offsets were. So we generate these rapidly and then hand that off to California Geological Survey and the USGS and others that are interested in mapping all of the ruptures. And at this scale, it's a little hard to see, but you can generally see some pretty fine scale ruptures. For the Napa earthquake, they were able to use the satellite data to identify ruptures that they couldn't see from the field crew just on the ground. And so this bird's eye view is really useful. And then while there wasn't a lot of building damage, they used the damage proxy map as another way to look at where the ground had been damaged or ruptured to identify surface rupture. There has also been a recent damage proxy map released in response to the Puerto Rico earthquake. So that's one of the first responses that we've had in 2020. How fast can we get this information? This is one of the key challenges with using synthetic aperture radar. It's not a continuous observation. It's not a daily observation. And so this timeline is an example of kind of how long it can take to get a first overpass following an earthquake, and then getting a product out after that. And so in the first earthquake in Mexico in 2017, there's a magnitude 8.2. It took 2 days before there was a first overpass from a Japanese satellite called ALOS-2, and then it was 6 days later before the first Sentinel-1 overpass came. And then it took us a while to generate a DPM because we had not generated a damage proxy map from that data set. But then when the next earthquake happened, in nearly the same region, or similar, also in Mexico, the first overpass happened within 24 hours, and because we had practice with the prior earthquake, we were able to actually get out the damage proxy map within 24 hours. And so it's somewhat serendipitous how quickly we can get this data out to the disaster response agencies. But looking ahead to the future and just kind of looking more globally, Sang Ho did an analysis to see, well, okay, what is the average wait time expected for an overpass following a particular disaster? So this is a somewhat complex chart, but basically it's showing that as we go towards the future, the wait time for an overpass from one of the available synthetic aperture radar satellites is going to go down. as more of these satellites are launched and as more data becomes free and openly available from these satellites, the wait time will go down, and we can look to a future where it's going to be expected that there will be a overpass within 24 hours. And so we should be prepared for that with our automated processing. So in terms of providing the data more quickly, there are a couple of things that we can work on in terms of further automating the processing, speeding up the processing with either machine learning or GPUs, and also articulating the need for this data in an urgent response mode, since it's typically been used for science mode and not needed very quickly, in order to encourage these space agencies to make this data available rapidly. So there are a lot of satellites up there, but there are also a fair number of them that don't have free and open access to the data. I'm running out of time, so I'm going to go a little bit quickly through the next couple slides. But I do want to point out that, Sentinel has really been a game changer. The next game changer that many of us at JPL and Caltech are working on, as well as people in the research community, is a future NASA satellite. So none of the data that I've shown you is actually NASA data. NASA is still yet to launch its synthetic aperture radar satellite. That is coming in 2022. That will be global. That will be free and open access. And so that will dramatically increase the amount of this data available and our ability to use it for monitoring. So keep that in mind when you're thinking about different future applications and what can be done. We're also working with other organizations, other universities. What's been a really fruitful collaboration with us is working with Earth Observatory Singapore. They're all the way across the world, halfway across the world. They have different end users and different communities there that are really hungry for this type of data. And so they've been really successful in taking our system, installing it, running these disaster response processing algorithms in response to floods and other disasters within Southeast Asia, and have been promoting the data there, and it's been found very useful. So in summary, I just want to say that this is a taste of what we've been able to do with synthetic aperture radar just within the last couple of years, just with Sentinel. There's a lot more data coming, and I think the applications from that data are just going to grow as the availability of that data grows as well. Some of these applications are related to disaster response. Some are more focused on monitoring. One of the things that has come up when we talk to different agencies about, well, do we really want to build a system that's reliant on this type of data? Is, NASA will say, well, it's a 3-year mission. But we're moving towards a future where between what the Europeans are promising and what NASA is committed to, we really can depend on or rely on long-term continuity of these types of observations. In the past, it's been a little bit of data here, a little bit of data there. I think in the future, we're going to have much more reliable observations from the different space agencies. And that will also help with this last issue about latency as more of this data becomes available. With that, thank you.